And hi everyone, my name is Aurora and this is George. And we took DRP last quarter with Alex. And so we're gonna present this together. And I will be talking about the first part and George will be responsible for the second part. And to begin with, our presentation, topic is on random graphs. And the language we use to describe random graphs is by their edges and vertices. And with the capital letter E represent edges, and the parenthesis follows it indicates which two vertices are connected by the edge. And B represents vertices, and we assume that there are no loops in random graphs, meaning that there cannot be an edge that connects a vertex to itself. So for all x, there cannot be EXX, and we also assume that the edges do not have directions. So for an edge that connects vertices x and y, we can also say that it connects y and x, so it is undirected. And now with our assumptions, we are able to construct a finite random graph. Firstly, we need to specify a set of n vertices and then add edges between them randomly according to a certain probability. And typically, we use 50% probability to decide whether an edge exists or not. And in this case, we denote as G, N, and a half. And however, we can use any number between 0 to 1 as our probability.
Let's try one with 4 vertices. Any volunteers? Let's say maybe if it's head, then there's an edge.
Sure.
There's its tail, it's nothing.
You could draw on the board.
Yeah, you can also draw, yeah. But this works.
Okay.
All right.
Your first one is tails. So.
First one is tail, so no edge between A and B.
Oh man, I got another tails.
No edge between A and C.
Come on. Heads. Okay.
There's an edge between
There
A
you
and
go.
D.
Tails.
Okay, no edge between B and C, I guess.
All right. Tails.
No edge between B and D.
All right, one more. Heads.
There's an edge between C and D. So this is our random graph with 4 vertices.
Yeah, and then we will give some examples about how random graphs are applied to show their importance. And so random graphs, they are widely used in the probabilistic method where one tries to prove the existence of a graph with certain properties. And by lemma, the existence of a property on a random graph can often imply the existence of that property on almost all graphs. And for the second application, it is on power grids. And where proposed strategies to prevent blackouts have been tested on tailored random graphs. And the power grid is typically modeled in this context as a weighted and directed graph with nodes, and the nodes are heterogeneous. They may represent generators or subnetworks, and the weight corresponds to the capacity of the transmission lines between nodes I and J, and each node was given a random number of half edges summing up to the correct total number of edges. And then these half edges are paired and connected to give different combinations. And another typical example is a data set of protein-protein interactions can be interpreted as a network by viewing proteins as nodes and the edges between them as the interaction between the corresponding proteins. And a classic application is to show that certain motifs were observed in the real biological network much more frequently than would be expected in a random graph with the same degree of distribution. And so these motifs were likely to indicate some special biological functions or design. And this demonstrates one common use of random graphs examples in molecular biology to act as a null model to be able to identify atypical and potentially meaningful topological features. Okay, and then after that introductions, we will delve into the properties of random graphs. So a crucial property of graphs is connectivity, and a graph is connected if there's a path from any vertex to any other vertex. So given a random graph with n vertices, we are curious about the probability that it is connected. And if n is large enough, it turns out that the graph will almost certainly be connected. The reason is that for a graph to be disconnected, it means that there exists a set of k vertices that do not have an edge with the rest of the n minus k vertices. So the probability of a random graph to be disconnected can be written as this expression. And since we are summing up k from 1 to n over 2, and this covers all of the cases where there can be 1 to n over 2 many vertices that are separated from the rest of the n minus k vertices. And for each k, we have c interest k combinations, and we require each vertex to have no edge with rest of the n minus k vertices. So the probability for such an edge, for such a vertex, is 1/2 to n minus k power. And since we have k vertices in total, so we add a k, multiply a k to the power. And this expression approaches to 0 as n approaches infinity. So therefore, the probability of a random graph being disconnected is very small with large n, so it's going to be connected. And another observation is that for two fixed natural numbers j and k, and for distinct vertices indexed by I to j and 1 to j and 1 to k, like x1 to xj and y1 to yk, we want to find another distinct vertex c that has an edge with each of the x vertices and none of the y vertices. And for a large enough n, a random graph will almost certainly satisfy phi jk, which promises the existence of such a vertex z. And the probability of a random graph not satisfying phi jk is written as this expression. And again, we choose j plus k vertices among the n vertices, and then we're going to choose j vertices like to be in the x set, and the rest of them will automatically be in the y set. And for any of the remaining vertices to have an edge with all of the x vertices and none of the y vertices, is 1/2 to j plus k power. So for it to fail the criterion, the probability is going to be 1 minus 1/2 j plus to the j plus k power. And since there are n minus j minus k remaining vertices, and we add a power of j minus n minus j minus k. And so this expression is going to be approaches to 0 as n approaches infinity. And this leads to a really significant property of random graphs, the extension property, and George will present that in detail.
So, the extension property is basically just a collection of all of the phi jk's. Well, this is too large for a finite random graph to satisfy. In fact, although each particular phi jk is satisfied by almost all of the finite random graphs. Although, intuitively, if we have a countable random graph, all of the vertices being all of the naturals, and it will satisfy phi with probability 1. So the proof is similar to the proof for the individual phi jk's. You use a similar argument, and notice that basically the probability of capital phi is basically a countable intersection of probability 1 events, so that the probability of phi being satisfied by this countable random graph is 1. This is very good intuition, but it doesn't give an explicit construction of a countable random graph that satisfies capital phi. So I'm going to present a explicit construction, and this construction uses two ideas. First one is to recursively construct a sequence of graphs, and then you take the union. And the resulting graph will satisfy the extension property. And this process is known as the Janssen-Savini process. And here's an image stolen from Wikipedia that basically gives you an idea of how an infinite random graph will look like. And moreover, so now we can refer phi, capital Phi, as a theory of random graph. And we know that there exists a graph that satisfies capital Phi, and it is also unique up to isomorphism. We can use a back and forth argument in logic to show this. I'm not going to present all of the details because I don't know all of the details. But so notice that capital Phi has a unique countable model and no finite models. And so the capital Phi, the extension property, or the theory of random graph is complete by the Washvault test. And here comes the most important theorem in this presentation. So for all first order sentences phi in our graph theory, it's either going to be true for almost all of the finite random graphs or false for almost all of the finite random graphs. And I'm going to present a sketch of the idea. So since our theory of random graph is complete, exactly phi or not phi will be consistent with our theory of random graph. And all of the sentences need to derive phi or not phi are true with probability approaching 1 for large enough n. So basically, if phi is exactly 1 of phi or not, and not phi is going to be true for almost all of the finite random graphs. And also we have a corollary from this idea. So a first order sentence is, in our graph theory, is going to be true for almost all of the finite random graphs if and only if it is true for our countable random graph. And here are some examples of the first order sentences in our graph theory. First one is about having a common, any two vertices having a common neighbor. And second one is no isolated vertices. Those two are going to be true for almost all of the finite random graphs. And here are also some non-examples. Our extension property is going to be a non-example because it's too big. It's not bounded, and the sentence has to be finite. And second one is connectivity, and the reason is that the length of a path could be infinite. Almost all of the finite random graphs are connected, and the infinite but countable random graph is also connected, but for different reasons. And the number of edges and vertices is also not a first order property. Like the countable random graph is going to have infinitely many vertices, but all of the finite random graphs are going to have finitely many vertices. And here is a little summary of our presentation. Firstly, we introduced finite random graphs, and we even constructed one with a coin that is maybe not very fair. And then we looked at some interesting questions. Do most graphs, in this case finite graphs, satisfy, first of all, connectivity? Or do they satisfy the phi j case? And then we talked about the extension property, and we showed that there exists a graph, an infinite but countable graph that satisfies this extension property, and we explicitly constructed one, and we talked about how it's unique up to isomorphism, and our theory of a random graph is complete. And then we introduced the most important theorem, the 0-1 law. And then we showed some examples or non-examples of first order sentences. We give special thanks to our project mentor, Alex. Here are some of our references. And thank